Hey guys, I'm back, and I have recently watched a video by a YouTuber named TechMath who specializes in making little math shortcuts that make math concepts easier. And I stumbled upon a particular video in which he estimated square roots, and I wanted to see for myself how accurate it is. So, basic underlying idea is that let's say you want to estimate the square root of 38. So what you do is you find the closest perfect square to that, which would be 6. So you estimate this to be about 6. And then you also have to add a fraction to it. And the fraction's numerator is simply whatever the number is minus the perfect square squared. So 38 minus 36 is 2. So the numerator becomes 2 up here. And then the denominator is simply perfect square multiplied by 2. So it's the 6 and 2 twelfths, which is 6 and a 6, or about 6.16. And getting a calculator, can easily find the square root of 38 to be approximately 6.1644140003. So, and since we got 6.16666 here, we can see that this is actually a pretty good estimate, but I just want to see exactly how good it is. So first off, I want to write this down in mathematical terms so that I can make this somewhat more rigorous, but at the same time I can also have something to put into a coding machine so I can get all of the estimations out pretty easily. So, the square root of a number n, such that n is as a positive integer, is approximately equal to the ceiling function of root n, which basically means the closest integer to the square root of n rounded up. So, for example, the ceiling of root 38 would be 7, since it's 6 point something something, which rounds up to 7 for the ceiling function. And then you subtract the ceiling of square root of n squared minus n all over 2 times the ceiling of root n if the ceiling of root n minus root n is less than or equal to root n minus floor root n. So for example, floor of root 38 would be 6. Floor of 27 would be 5, so on and so forth. Or, it's also approximately equal to the floor of root n plus n minus root n quantity squared, all divided by 2 floor root n otherwise. And so, here it is in all its splendor. So, now what I'm going to do is I'm going to code it and see what all it returns for numbers from 1 to 100.
Okay, so now I have JavaScript open, and what I'm going to do is I'm going to write some code that will allow me to see what the estimations from 1 to 100 are. So I'm going to say for a variable I is equal to 1, I is less than or equal to 100, I plus plus, which basically means that for the variables 1 through 100, for the numbers 1 through 100, we're going to let a variable j be equal to the square root of I. We're going to let a variable k be the floor function of j. And we're going to let L be the ceiling function of j. Okay. And now we're going to say that if L minus j is less than or equal to j minus k, which is essentially what I have written for the algorithm, Okay, I should add this here. Then we want to return L minus the square root of L squared. Should probably be spread out. L minus L squared minus I. I think I also want to have that POW minus I. And then divide that by 2 times L. Okay. Have that. Else. Then console.log k plus quantity I minus math.pow k2, and then divide that by 2 times k. Do that. Okay, that's looking good. And then close that off and rerun it. And here we have all of the estimations using the algorithm. This is what this returns. Now I want to see how good these actually are. So now what I'm going to do is I'm going to reset, and I'm basically going to keep the same thing. I'm going to create a code that allows me to find the error using, the error of the algorithm, I++. Basically the same thing. I probably didn't have to delete that. jmath.pow. Okay, no, screw it. I have the error code right here. Basically the same stuff, except now it returns -1 times j minus L plus L squared minus I all over 2 times L. This basically, all that's important is that this code does work. So just gonna paste this here, let it run. And then, yep, it's got all the errors right here. I'm not sure why it says -0 for this, but okay. But like, see, here it goes 0.01, 0.05. So like the highest error that I can visibly notice here is only 5%. And then it seems to be getting better as it goes down. So next what I want to do is plug all these into a calculator and find some kind of model for the regression. So I'm going to input all these into a scatter plot basically, and we'll see where things go from there.
So as you can see here, I have taken the liberty of inputting all of the numbers from the error code into my calculator. So what I'm going to do is zoom 9, and then here we have a scatter plot of the data. And what this appears to me is that this is appears to be some kind of sinusoidal regression, such that no number is negative and that it appears to be going to 0. And if I can prove that this is going to 0, then we can see that this error is really, really small as x gets infinitely large, and that this is indeed a good estimate for square roots. So let's see what this could be. Okay, so based on the curve that I got from my regression, it appears to be some kind of sinusoidal regression of form sine of ax plus b plus c, a times sine of bx plus c plus d, except I want to find a way to not only decrease the amplitude, but also increase the frequency, because that's what appeared to be going on in the regression. So I think the best way to do this is let a be equal to 1 over a polynomial q of x, because that would help reduce the amplitude a lot as x gets larger. And then we also let b be a polynomial p of x, because that would also increase the frequency as x gets larger. So we can rewrite this regression in the form of the absolute value of sine of x times p of x plus a all divided by x times q of x for some polynomials p of x and q of x. So now what I want to do is find the limit as x goes to infinity of this expression. Okay, and we know that for all x, there's a number b such that negative b is less than or equal to sine x times p of x, which is less than or equal to b. And therefore, or also we know that the limit as x goes to infinity of 1 over x times q of x is equal to 0, since q of x is a polynomial. And therefore we conclude by the squeeze theorem that the limit as x goes to infinity of sine of x times p of x plus a divided by x times q of x is equal to 0. So what I just did is I found a basic model for the error regression, and I've shown that it goes to 0. So this, the algorithm mentioned up here, it does get perfect as x tends to infinity. So yeah, this was a fun project to do, and I think my only regret basically is that I wasn't able to find polynomials p of x or q of x such that this model would fit my error regression. But other than that, I think we can conclude that this is a really good model for estimating square roots. So I hope you've enjoyed this project as much as I have, and thank you all for watching, and have a nice day.